impressed anyone's still here. See, I'm on West Coast time from the United States, so it's like the middle of the day for me. So I'm going to have a whole different energy level here that I hope I'll extend to you. So thanks, everyone. As I said, my name's Dave Weston. I'm a VP of Operating System Security at Microsoft, which means I no longer have any technical talent, but I sign lots of expense reports. That's the main job. I love coming to Israel. Been here many, many times, over 20 times. I think I have the record for the most visits to Israel and still not learning any Hebrew at all. I know 3 words in Hebrew: Todah, Sababa, and Arak. Those 3 get me through my whole time here. And I came in on Monday. It was amazing. I landed at the airport, got in the cab, driving along, and so many people were on the highway there to greet me, cheering. It was great. So excited to be here in Israel. It's never a dull moment, always something exciting. But of course, BlueHat itself is the most exciting. So I'm here to talk to you today about some of the security work we're doing in Windows 11, some of the things we've gone along with the journey. But most importantly, I'm here to show you a ton of new stuff. In fact, I told my team, let's not announce that here, let's not announce it there, let's announce it here in Israel, where I think people will be very enthusiastic and excited to see some of the things we're doing in Windows. And also, when people get mad about the stuff I'm announcing, I need you to have my back. So we'll make it work. All right, so with that, let's go. So in Windows 11, we have a strong and distinct security strategy that I think is bold, and I think those of you who have been working on security for a long time will be impressed with. Even James, I think, by the end of this talk will be like, Microsoft's serious about security. Watch, well, you'll see. So there are 3 things that we are really inputting into Windows security. The first is the hardware security baseline. I am the person who infamously required the TPM, and by the end of this talk, you'll be like, Dave did the right thing. Sorry, not sorry. So a hardware security baseline is there to provide the ingredients and the primitives we need. Secure key storage, high integrity measurements for things like boot, and secure key release. We also have things like virtualization-based extensions and other things that are required to have a trusted execution environment. And we'll show you how we are using that trusted execution environment, TPM, and the other parts of the hardware security baseline to solve some of the most important problems in Windows and some of the most long-standing by the end of this talk. The second, I think, big philosophical change that we've had in Windows is we no longer credit ourselves for things that are not on by default. I'll say it again. If it's not on by default, it doesn't exist. Why did that happen? Well, our strategy for Windows 10 was we're going to pack this thing with security features. We're going to have all the guards in the world, every type of guard you can imagine, notepad guard, you name it. How often did people turn that on, do you think? All of you work in cybersecurity, how often do people actually override the defaults? Never. So our new ethos is basically, if it's not on by default, it doesn't matter. And you'll see that we are rapidly and aggressively turning on defaults in Windows 11. Examples, multi-factor authentication with hello is on by default, BitLocker. We've turned on things like LSA protection by default. Virtualization-based security is on by default. We'll keep going. And finally, I think the most important philosophical change, and I hope you'll agree with me at the end, is we are no longer avoiding the hard things. So 2 big things I'm proud to talk about today are we'll be enforcing code signing in Windows over time with features like smart app control that will mean malware will at least have a much higher bar to get onto the machine. You'll have to be signed, we'll have attribution, the ability to do revocation. I'll also talk about how we are going to migrate away from administrator all of the time towards standard user. And UAC will never be mentioned in this talk at all. I love the clap for that, by the way. I see you. I see what you did there. So what are the really big rocks that we want to work on? First, running as admin. I call that running with scissors. It's a little bit wild that in 2023, we're still basically running as root on Windows. And I think all of you know the impact for that. You're 1 click away from doom. And if you're on a connected network, which almost all of us are, You're one click away from doom that leads someone to having domain admin. We've got to change that. It's a very hard problem. I'm going to make you all see how hard it is by the end, but it's something that we are going to tackle head on. The next thing is what makes Windows Windows and not some of these other platforms is you can do what you want with it, right? You can grab that Winamp from 1997 with just the perfect skim and all those extra stack buffer overflows, and you can still run it if you really want to. You can run Minecraft and download every random downloadable content in a compressed RAR file if you want to. The challenge with that is the thing that makes Windows Windows and so useful and valuable to billions of people is also the thing that keeps most of you employed. And so we've got to find the right balance of keeping Windows Windows while also making sure that we're tackling some of these security issues that come from the need to have compatibility and decentralized apps. If I just said, hey, next week, all of you have to get apps from an app store on Windows, you probably wouldn't be happy. So we have to find alternative mechanisms to get towards security. And then finally, I've been working on this problem for 20 years. I don't want to work on it for 20 more years, but memory safety continues to be a big rock in Windows. Our previous strategy was really to target not so much the bug primitives, but the exploitation primitives on the operating system. So we looked at things like control flow integrity for targeting return-oriented programming concepts. We looked at things like ASLR for making non-deterministic memory addresses, data execution prevention, et cetera. While those were helpful technology at certainly slowing and driving up costs, we're certainly not satisfied with where we're at on disrupting exploitation. And so over the next several years, you're going to see an aggressive and meaningful pursuit of memory safety. David, Sar, and many other people worked on some incredible research with things like Chariot, looking at capabilities models around architecture. I'm going to tell you today about how we're using Rust on the operating system along with other constructs to solve this problem. I'm going to guess this is a security crowd, so there's some few fans of Rust in the audience. I know what you want. When I decided we're going to do some talks here, I was like, I'm going to announce Rust in the kernel here in Israel. So I thought folks would be excited about that. So it's good to hear that. All right. So let's talk a little bit about the road to adminless Windows. I put Windows 2000 in here because of this whole amazing 90s theme, but I bet very few in this audience have actually, besides probably Mark and myself, have actually run Windows 2000, but I love the theme here. So let's talk a little bit about how we get to adminless. You've heard this concept of passwordless. That's the industry slogan for things like FIDO2 and passkey. The slogan that I have, if you're going to make a revolution, you have to have a slogan, and that slogan is adminless. We want to get to a world in which not everyone is running with full admin rights unless it's absolutely required. Getting to default is one of the core issues on Windows, but there's some challenges there that we have to tackle. The first thing we want to recognize is removing admin capabilities by default has immense value. Actually, many of the technologies in Windows tried to work around that problem. UAC, the whole concept was, let's work around not having to be standard users and some of the challenges around that. While UAC is a useful and valuable technology, it certainly hasn't solved the problem of deprivileging or making attacks that require admin privileges much more difficult over time. We've also had to build other features, things like protected processes, which, again, is not a security boundary because it relies on the user not being able to modify the kernel. We have things like virtualization-based security, which we had to introduce a whole other kernel, secure kernel, because the admin to kernel boundary is not permanent. So we've had many tries at saying, let's not tackle the core problem of having everyone run an administrator. Let's build other security technologies that try to compensate for that. I'm the first to say I like to own decisions. I don't think that was the right decision. We're going to go back to the drawing board, which is, first principle, let's run with as least privileges as possible, and we can do that, and I think we have a good plan that I'll talk to you about. The other challenge that we have is there is significant debt within the operating system that makes running as a standard user very, very challenging. My favorite is to change the color profile on your monitor. You have to be admin. To modify basic firewall rules, you have to be admin. Ask me how I know. I'm one of the few people that run a standard user. So there are many places in the operating system where we make assumptions, frankly, for our own convenience about necessitating administrator, and that's something that we'll have to change to make the user experience even possible, and it's one of the reasons most people don't do it today. The other massive problem is most apps on the platform, on Windows, are Win32 apps, and the vast majority of them are overprivileged. How many of you have written a Windows app before? Any kind of like basic tool? How many of those apps didn't require admin? You probably don't even know if it does or not, right? It's like, I don't know. I called some API, I don't know what it requires, what some SID. So that's a big issue. There's just been an accumulation of debt. Most of the useful apps implicitly or explicitly require admin, and all of those apps will need to be removed, have privileges removed over time to make the experience of actually running not as admin valuable. So again, a very challenging issue, but I'll show you how we're trying to tackle that. Okay, so one of the core issues is this concept of Win32 apps being overprivileged. This is, again, a little bit of Microsoft's fault in the sense that we have not really made it easy to sandbox your app. In fact, App Container, which has been talked about a couple times today, is our sandboxing platform, or at least low-level API primitives for deprivileging an application, but it was essentially tied to our Universal Windows platform, our UWP apps. Most app developers did not choose to go UWP, and as a result, most apps are not sandboxed. So we're, again, looking back at this hard problem and deciding we need to make a viable framework to isolate apps on Win32, and there's a couple of different principles that we need to get towards that goal. The first is, obviously, we want strong containment, but there's a balance. So for example, many of you in here are probably fans of things like granular system call filtering. I don't know if we're going to get the compression utility day one to filter every argument towards a Win32K system call, right? So we need to be sort of realistic about our containment goals and provide enough value without complexity. The second principle is developer simplicity. I can tell you, working in this ecosystem for a long time, developers don't necessarily want to change their apps. And so just because a bunch of us security people think things are cool does not mean a few thousand developers are going to go rev their apps overnight unless it's dead simple and the value proposition is clear. And again, back to first principles, that means not having to write a sophisticated eBPF-based filtering for your system calls to get things to work. Just never going to happen. Nobody wrote SE Linux policies in 1999. Nobody's going to write those today. And then finally, isolation cannot be super annoying. Many of you have probably used different operating systems where you're getting camera pop-ups and persistent requests for files that you have no context on. If you do that en masse for billions of users, they will simply revolt and go use a different operating system or different version. So we need to make the first two principles, containment and developer simplicity, while also not annoying the users. And this is what I think we're trying to achieve in Windows 11. So how does this app isolation work? Well, I already hinted it starts with app containers, and it starts with the concept of low IL, which is not too dissimilar from what we've done in UWP, and provides basic isolation primitives for applications in Windows. On top of that, we are building on what's called the MSIX framework. MSIX, in a nutshell, modernizes Win32 by using file and registry API virtualization to shim calls that would be, sort of arbitrary paths on the operating system into a app-specific storage. This is really there for things like clean uninstall and reinstall, app roaming, backup, etc. But it's also a very convenient construct for isolation because we can write most of the app state into a place where the application doesn't need additional privileges. So we can assume, hey, from day one, birth of your app, from default, you only need to write to this location, which makes things very useful for the next step. The final step, which is net new, is brokering on the file system. So we're actually introducing a mini filter driver that will provide a brokering mechanism for file system access for files outside of the app's default access. What does this mean in a nutshell? Well, in the UWP world, one of the challenges with adapting or the app container to Win32 was we assumed usage of WinRT APIs. So for example, if you were running an app container previously and you wanted to access the file system, you had to replace all those beautiful Win32 APIs to, calls to create file X with WinRT, async, return, file broker picker, very modern C++ concepts. But for those stodgy folks who are writing Win32, they're probably not going to do it, right? Back to first principles. So what we're doing with this new system is using a file system driver to enforce access to the file system using traditional APIs. But once the application is launched in this app silo context, the file system broker will manage access. And that becomes much simpler to write very basic policies without changing substantial parts of your code, which is going to be helpful. OK, so how do you do this? It's actually really straightforward. To convert something to an MSIX, you need to do a few basic things. You need to create a manifest so your application has an identity, and we know the context in which to run it. So you need to be able to say, hey, I'm going to create this MSIX. It's going to have an application identity, which we can use to enforce access across to different APIs and resources across the operating system. And it also allows the create process and kernel to figure out that the application needs to be launched in an app silo context and what privileges it provides. So in this very simple example, we can actually take Notepad++ with 0 to small code changes and repackage it in an MSIX, very simply. We then, under the hood, have generated a manifest that says, let's run this Notepad++ app in an app container and app silo. And we will give it an identity, which in this case is called preview security. Very simple, basic concept. Now, the problem is, by default, the application developer will have no access, which is kind of the point of the sandbox. And traditionally, one of the challenges with writing a good policy is that there's a long tail of knowledge and code paths that you require as a developer to understand what resources an app may or may not need. The way that we're solving that problem with this Win32 app isolation framework is we're providing a capabilities profiler, which uses ETW events to trace sort of this audit mode of a developer's path so they can run through their average user test cases. They can ship the app and ask their users to provide back traces. We will then analyze those traces and produce a proposed app isolation policy. So for example, if your app needs access to the documents path and you don't know that a priori, your users would go and run this for you. You'd run through your test cases. In the traces themselves, we would see that that's a required path, and then we would add that path into the isolation manifest, and the file broker would grant access to file handles in that requested path. That would also occur for things like registry items, COM objects, et cetera, et cetera. Now, is this the optimal way to really lock down a sandbox? No. But in a way, it's a democratization of sandboxing. We don't want sandboxing to just be the domain of Chrome or Adobe or Office. We want most people to be isolated, and then over time, they can use this sort of open policy and reduce it over time to get stronger and stronger. So we've produced a tool along with the isolation framework that makes it much more practical to create a policy. So what are the other features that we have? Well, in the sandbox, we actually have roughly feature parity for what most things would exist in Win32. Now, I say roughly because there's a zillion APIs, and I don't claim that we have one-to-one parity, but for key use cases, it's true. We have implicit brokering. We have manifest extension support for things like file type association, so you can associate your app, things like automatically launched COM servers that you might need for things like DCOM, and you can use both modern and classic context menus, which makes it more viable for modern apps. We also support things like drag and drop, printing, systray icons, and very cool, if you decide you don't want an application to have permissions, you can actually go back and revoke specific permissions, which is something that I've wanted for a long time and is especially critical for those of you who are privacy conscious. Not that anybody in here minds having access to camera or microphone, right? All right, so let's check out a demo. This is going to be the most boring demo in the world, and that's on purpose. I don't want you to even notice this application is sandboxed. So if everything goes well, I'll click this. We're going to launch from a context menu, Notepad++. Also show you that we can do file associations in an app silo. This is Notepad++ with no code modification running in an app container. We can preview files. We can drag and drop with a basic manifest. And we can go back, reset, or revoke any of the file system permissions from the app from a simple UI. Yeah, it is pretty cool, right? So how many of you like right away would go Sandbox Notepad++? I would, yes. I've been running it for a while. So this is cool. Again, I'm not saying this is optimal from a security perspective. Obviously, there are many, many other ways to lock this down more. But again, I need you on board with this. The goal is not to always optimize security. It's to get people started. And if your average app developer, again, is not going to write an eBPF, complicated policy, they can at least do this. And this will prevent a large set of attacks in case the application is compromised, which I think is massive progress. Now, the reason, right, we want to get all of these applications in Sandbox is not only because that's more secure and we have containment, and also if we can get the vast majority of applications to a Sandbox that don't require admin privileges, it's a much smoother path, right, towards standard user and enforcing that mainstream. And we all know running as admin is like running with scissors pointed right at your face. When you trip, it's not going to be good. So how do we get there? Today, standard user is pretty difficult to run in. You don't have admin rights, so you can't install drivers. So even myself, occasionally, I'll plug in a camera or something, something that requires a kernel driver or a driver running its system, and it's a bit of a pain. You can't elevate today, at least in very simple circumstances. You can't write policies that say, I just want to elevate for a short period of time for this specific scenario. That's why we have so many PAM solutions on the market, at least for enterprise folks. For home users, they don't even have PAM as a possibility, which is rough. And obviously, it protects from malware and user mistakes. And what we mean by user mistakes is you just don't have privileges, so you can't make the mistake. Where we want to go in the future with adminless is a modification of this. We want the ability for the user to just-in-time elevate to admin for specific use cases, but not have the ability to run as a persistent admin. So you can elevate, with proper authentication or authorization for something like a driver install, but that would be temporary, and then those privileges would go away based on a specific policy. So we non-persistent admin rights. We also want to move away from using password-based solutions toward using bio, both for security reasons and mostly for user experience. So today, if you run as standard user in Windows, we actually default to username and login for every elevation. Probably few people do this in here, but the fourth time in a session that you get asked for your creds to elevate, you're going to give up and switch back to admin. We need to make sure that we're addressing that by making that less frictionful. And then this world does not protect from user mistakes, obviously, because the user can elevate to admin anytime. The user can, if they want to, shoot themselves in the foot, but it does protect from malware or other automated or deterministic methods for using that require admin passwords, or admin credentials. So for example, exploits under the hood that want to go dump LSA will not work in this scenario unless the user explicitly authorizes that action. And the cool part about this is it, again, democratizes running as least privilege, because you no longer need a sophisticated PAM solution, although this can work with PAM as well. So, a couple of basic concepts for this approach. You would select this approach in the out-of-the-box experience during install. You'd say, hey, I'm ready to run as secure as possible. We'll generate a shadow non-interactive admin account. We're also going to make a pass, this is underway now, to go across the operating system and look at common user operations that require admin today that either don't need to be admin, or conceptually we could turn into a different privilege group and grant it by default to this new adminless user. We are making Windows Hello work for creds for elevation, which I can tell you is a joy. Just using your face to elevate is so much better. And then we are working across the ecosystem with the top third-party apps to remove unnecessary privileges. So for example, one of the things we just worked with was actually a Microsoft app. Visual Studio has removed the need to have admin privileges just to run. And there's a long list and probably several years of work here. So the elevation in user experience, as I said, defaults to bio. So it's as simple as double-clicking an exe that requires admin privileges and either using a fingerprint or face to allow those changes. And here's a bit of a mock-up of what the UI could look like in the next version of Windows. These capabilities are coming to Windows in short order. You will have access to the Win32 app isolation after this year's build conference, and we'll have a GitHub with some of the capability and profiling tools. We're calling this a preview because it's not on by default in the operating system yet. What we're trying to do is give developers a chance to go and get their apps ready to go for when we GA this functionality. But as security researchers, I'm sure James won't look at this at all. But for security researchers who want to go and poke at those things, obviously it's going to be within the bounty, and there's going to be a lot of experience. So this will be fun. And like I said, it'll be coming at Build 2023. And then with adminless Windows, it'll be in a future version of Windows. We're actively working on it now. But it's important that we get the Win32 app ecosystem to reduce privileges so that we're ready to go adminless, and that's a clean experience. And this is going to be our approach for solving one of the most long-standing issues, which will help with all range of security issues from malicious drivers to dumping creds from LSA and everything in between. So excited to see this coming. Now, I want to talk about how we're addressing a few of the other core problems in our protecting the platform strategy. So 3 major platform issues that we're tackling head-on from a security perspective are app signing not being required on Windows. One of the reasons we're in this whack-a-mole with things like antivirus is we can't do real attribution or revocation of apps. So if a developer makes a malicious app, we can block the app, but not the developer. The concept with signing, at least when you have proper identity proofs, proper CA, et cetera, is if a developer has to sign an app and provide a real-world identity, whether that's a business entity or a user, if they introduce malware or some other nefarious application, not only do you block the app, but you block the individual. And if you have a functioning CA system, that individual should not be able to come back the next day and get a developer signing cert. They'd have to do more sophisticated real-world things like passport faking or other kinds of things to get a certificate. Now, that's obviously not perfect, but it's a heck of a lot better than writing a bunch of YARAs and trying to track every possible opcode sequence for the same representation. So this is a very important step forward in securing Windows. The second is comprehensive credential protection. Obviously, removing admin will help a lot with very common, Mimikatz and other LSA dumping tool approaches. But as we move to more modern authentication types that use things like bearer tokens delivered by cookies, we're seeing more and more attacks in this space, and Windows needs to evolve the platform to address those. And then finally, security processor fundamentals. While the TPM has been great for a number of these scenarios, everything from secure boot to being able to store keys, the TPMs themselves are not in the most healthy state. Many TPMs are vulnerable and not updated, or in states of dysfunction based on a number of different factors. And so things like Microsoft Pluton coming into the ecosystem to provide a more consistent experience is a big bet we're making. So I want to talk about smart app control. This is our attempt to, again, democratize what's been used in the enterprise for a long time as a very powerful approach, and that is writing an application control policy based on code signing to either to allow or disallow specific apps. So what Smart App Control does is it auto-generates a policy under the hood using WDAC based on what the Defender Cloud sees as the most commonly used apps. In a nutshell, you can think of it as monitoring the top apps in the ecosystem that are used by millions of users and not known to have any nefarious issues, and then generating that policy as a baseline for app control. What that allows us to do is say the vast majority of apps, at least for common consumer users, will just work. And any application that was auto-generated, just in time by an attacker using a packer or something like that to evade AV will not work. In addition, applications that are signed by entities that have an established reputation or trust that we assign based on reputation, again, in our back-end cloud, will not run by default. They will have to generate trust or reputation on other platforms like Windows 10 or Windows 7 before they'll be allowed to run. The reason we went with this approach is we do not have a centralized app store that we're willing to push everyone into. There are many complexities with doing that, interspersing security with like business and revenue. And also, one of the powerful constructs of Windows that I think most of you agree with is, I want to get my apps where I want to get my apps. If I wanted to download the app from a torrent client, I should be able to do that. If I want to pull it from a file share, I should be able to do that. If I want to download it from a website, I should be able to do that. So what Smart App Control allows us to do is enforce powerful, proven application control approaches without the extra work of having to generate a policy and without the work of forcing every application to be in an app store, but it provides similar security value. In addition, this is something that I think many of you will like. When you're running in Smart App Control mode, not only are you using this policy that's auto-generated by the cloud, but we also block all scripting types from the internet. So PowerShell, PS1 scripts, LNK files, all of the things you would associate with kind of fileless or living off the land style attacks will not run if they come from the internet. Yeah, it's pretty powerful. So it's taking the Office construct and applying it to Visual Basic scripts, etc. I often gleefully download hashes that people put on for the latest LNK to VBS to PowerShell and back and forth. And I will tell you, this is a very effective against those style of attacks. And so we're excited that that's there. Now, this is obviously not for everyone. Many of you are Empower users here and say, Microsoft, get out of my way. Cool, no problem. Go in settings, turn it off. You don't even have to reboot. It's just there. So we're giving a lot of flexibility around this, right? So we're taking some of the values from things like S mode and making it easier to deploy. So here's a great example of a real-world attack. In this case, it was a DLL that was found. Defender had partial protection. Took about 36 hours for the signatures to pump out worldwide. In between being aware of this malicious file and a signature being available, about 5,000 devices were infected. Smart App Control, which is now on by default for many users with the latest release of Windows 10, in this particular case had no infections. And that's because the DLL itself has no reputation. So even though it's not known to be malicious a priori, it simply hadn't got enough reputation. And this is what we expect to be the commonplace. Now, again, we talked about how this is probably not for every user. If I rolled this out on all of your machines and IDA didn't start up with your favorite random plugin, you'd probably be mad at me and tweeting me. And so what we're trying to do is use AI not only to generate the policy, but also to determine whether this machine looks like it should be turned on. So the way Smart App Control works is if you clean install Windows 11, we'll run in audit mode for about 30 days or so, and we'll look at the tools and other applications that run in your system. If you're running things like IDA and hex editors and things like that, you're probably not a good candidate for this getting flipped on to enforcement, although you can do it yourself if you want. If you're just cool with Chrome and a VPN client and some Netflix thing or whatever, Spotify, cool. You can run with App Control, no problem, and you're protected from a lot of things. So again, this is to avoid things like dialogue fatigue and all the annoying stuff that you would probably revolt against if we actually enforced. And so the hard, I think, value of this feature is finding that right balance. It's not the optimal security. You can go in and write your own policy if you want. You can get hardcore. This is not about being the most hardcore. It's about targeting and, again, democratizing good security technologies. So we expect with this first rollout to hit roughly 20% of users in this enforcement mode, and then over time ratchet that up as we get good results. So the next thing I want to talk about quickly, because as usual, I've packed this with way more stuff than I have time for, is our Pluton security processor. Actually, the machine I'm presenting on now has Pluton. And this is our security processor designed by Microsoft based on the Silicon IP that's been used in things like Azure Sphere, which is a super secure IoT device, as well as Xbox. We designed it in Xbox to be resilient to physical attacks, the threat model of Xbox, and I encourage you to go back to, I think, BlueHat 2019 Seattle, where Tony Chen talked about our threat model and how we build the Xbox for physical attacks. We worked with processor companies like AMD to actually integrate this on die. By moving this on die, we reduce the attack surface of what you can do physically against things like buses and fault injection, et cetera. And so we actually are more resilient to physical attacks, which helps a lot. But the major advantage from my perspective with Pluton is Microsoft writes the firmware and can keep it up to date. The huge problem in the ecosystem that Microsoft sees through our own data and telemetry is that while TPMs are super valuable for things like multi-factor authentication and required for FIDO2, hello, key storage, you name it, many of the TPMs out there are in states of disrepair, either out of date because the OEM manufacturer didn't onboard firmware updates to Windows Update. So the firmware, those updates may be out there, but they're not installed on a good chunk of users. Or the hardware itself is coming to some sort of disrepair. Firmware issues, hardware issues, et cetera. So when we have this large set of basically malfunctioning TPMs and no way to fix it, Pluton is our approach to getting more consistency in the ecosystem. So Pluton is designed by default to be easily updatable in a high integrity and secure manner from the operating system. That's a design goal. And so with Pluton, you can get firmware updates automatically for Woo as long as you have a processor that supports it, which is in 2023 it might sound like table stakes, but obviously it's critical. The second thing that we think is very important for Pluton is we are moving towards, you guessed it, memory safe language with Rust. We're not there yet, but it's something we're working on. Thank you, thank you. Last month, there was actually a really, really interesting issue. I think, if I'm not wrong, discovered by Quark's lab. It was a memory safety issue in all TPM, roughly a good chunk of the TPM reference implementations out there. So those types of memory safety issues in the trusted computing base are real, and they arguably are some of the most painful. Not only because if the TPM is compromised, you have potentially access to all sorts of things, but TPMs themselves, when they have to be updated, can sometimes have to reset state, and it's very painful for the user. So having something like Rust for memory safety there is super critical, and we're working hard to realize that. We're also making Pluton easy to use across the operating system, so common key manipulation and crypto APIs like Encrypt will actually have the ability to use Pluton as a key service provider, and very importantly for the next slides, we will actually provide in the future the ability to protect things like PRT tokens and other modern constructs directly in Pluton by integrating with Azure Active Directory and Intune. So I want to talk about a larger problem we're seeing, particularly in cases like SolarWinds, of increasingly targeting OAuth and other bearer tokens that come from cloud service authentication, like Azure Active Directory. So today, they are much smaller than, say, NTLM theft, at least in the credential theft telemetry we have, but there's still potentially thousands of instances. Azure Active Directory reported over 60,000 token replay attacks in February 2023, which is an increase. And the potential damage of a successful bearer token replay attack might be bypassing conditional access, strong auth, or other common controls that are based on authentication, which is a huge concern especially for for enterprise customers. So I'm going to breeze through this. I think most of you will be familiar with this, but a standard bearer token request to Azure Active Directory starts with a long-live auth request to Azure AD, where you may have MFA or other proofs required. That response comes down with an access token and a refresh token. That refresh token can be used to powerfully derive tokens for different things, for example, apps or app scopes or policy scopes. And then you can make additional requests for applications like Office 365 using that access token. I'm going to have to speed through this, but this is a hierarchy of the different credential material that's involved both in sign-in sessions and app sessions. I think the important piece for this audience is getting access to the primary refresh token will enable you to get authorization for most things that that user has access to, and it will be tied to the credentials in which they signed into the machine. And that is true for both native and web applications using AAD. If you're familiar with folks like Dirk Jan, who has a tool called Road Tools, which is a very powerful tool set, we're seeing more and more, particularly state actors, using those tool sets to attack folks using federated identity like AAD-SSO. So solving this has become a very important problem for the platform. Token theft looks like this. You can intercept the request using a proxy. You could be a malicious insider or a piece of malware, just taking those directly off the machine. That's why storing them in hardware makes a ton of sense. Or in some really terrible cases, you may see server logs logging these tokens. They can then be replayed. The reason you might want to replay these is if you want to attack a network, for example, that has EDR or XDR or whatever DR that is popular these days, and you would like to avoid being detected, you might use tradecraft to get onto the machine, immediately get access to a PRT or an access token, and then take that credential material to, say, a VM somewhere in the cloud that doesn't have visibility, and use that to log into the cloud. We saw that tradecraft in SolarWinds attackers, and we've seen it across the board. It's becoming more and more common as zero trust solutions become more critical path. Attackers don't want to get caught. They want persistent access. So it's now become really important to use these tokens off box in order to avoid detection. So as a result, we've come up with a token protection approach. It's actually quite simple. For that initial login around the PRT token, what we're using is a cryptographic approach to bind that PRT token to the device using TPM and virtualization-based security to that device. So that means that PRT token, once it's issued and authentication happens, it cannot be taken to a VM in some foreign country across the world. It can only be used on the device that has that hardware. Now, that doesn't stop you from proxying malware or other things, but it does stop that specific instance where you're trying to avoid zero trust or visibility on the device, and you will have to operate on the device in which the token was issued, which is very valuable. Device registration, again, will just include you setting up initially your device for that initial login. You'll get device and binding root keys. And then token sign-in sessions in the future will be predicated on using or having access to keys that are now stored in secure key storage. The solution we're working on today is based on virtualization-based security. It's called KeyGuard. KeyGuard is a nice blend of hardware-based security with increased performance over the TPM. And so as we work on making Pluton and other processors more capable, we're using virtualization-based security today to protect that key and bind it to the specific hardware. Keep jamming. So this token binding approach is supported in the operating system today. For those of you who like to dig around in headers or public files, you'll actually see encrypt and all of the standard key storage APIs actually allow you to pass a constant to store and manipulate keys in virtualization-based security. So all of the primitives from an operating system perspective are there. And we are looking at broader support in things like Azure AD over time. It's currently in private preview and expect that to expand in the next year or so. So again, this is a really important step in protecting modern bearer credentials on the Windows platform. And I know none of you care about this, but for the last segment, I'm going to talk to you about all the cool stuff we're doing with Rust. So memory safety in Windows is important for a bunch of reasons. First, it's the dominant MSRC and bug primitive that we get across the board. So again, all of these vulnerabilities are opportunity for exploits. We think of them as potential risk and exploits as actualized risk. And over time, we've learned that as we've targeted exploit constructs with things like XFG, CFG, or anti-exploitation techniques, we think we've run out of steam on ways to stop exploit techniques, and we need to move our focus to bug classes. So we have a challenge of the general linear growth in the number of memory safety vulnerabilities and a reduction in viability of our exploit mitigations, which means we're in a bit of a trough and need to relook at our strategy. Our strategy is to increase investment in bug class elimination, but so far that's been incremental. That means we've done things like automatic variable initialization for stack variables on the compiler. Very cool, but that's a narrow bug class. We've done things like introduce type safety with for casting types. We've introduced protection with things like CastGuard that help with, again, very similar bug classes. But we're talking about a few percentage points across the board, not the kind of progress we want against such a big problem. And that's caused us to rethink our strategy. So there are really 3 tools in the toolbox for memory safety in Windows. The first is memory safe languages that can be the safer versions of C#, which we call System C#. That could be Golang, or more commonly Rust. I'm sure people will be excited about Rust. The second is architectural changes. David, Sar, and other folks have introduced how powerful things like capability models can be on the CPU for taking existing native code, modifying operating system constructs like allocators, and then producing very viable memory safety for existing code without having to rewrite the world. I hate to tell you, I know Rust fans out there, rewriting Windows and Rust probably isn't going to happen anytime soon. So while we love Rust, we need a strategy that also includes securing more of our native code. And then finally, an approach that we haven't experimented on, but I think Sar and other folks have pointed out some of Apple's good work, that is doing safer subsets of the languages. So for example, at Microsoft, on the Azure Sphere platform, we support a thing called Safer C, which introduced some constructs around spatial safety. The C++ working group has some really, really cool functionality, things like GSL span classes that guarantee memory safety for things like array accesses, and so on and so forth. Apple, in their iBoot, I believe, has a thing called Firebloom, which is a safer type-safe subset and uses a type-safe allocator. So those are also viable tools. But today I'm going to focus on memory safety in Windows and our early experiments. So the first thing that we introduced with Rust, at least in Windows, is Dwrite. How many of you think font parsing is scary? There's this thing called Dooku. I don't know if anyone knows about that. That had some font bugs. So obviously, Dwrite font parsing is a critical attack surface for memory safety that we want to target. So it's one of the first things we looked at applying Rust to. The second is, again, this component I'm sure none of you know about called Win32 that may or may not have bugs occasionally. And that's been another place that we're looking at using Rust and memory safety with. So we're going to talk about those today. The first thing I want to say is this is not my work. This is the work of folks like Arden White and Chris Lung and other folks back at Microsoft who have just been the most staunch advocates of Rust and have done way more work than they ever dreamed to make this a reality. This is really a passion project to get this much results this fast, so I want to acknowledge those folks. I'm just lucky to be representing their work. Yep. So we're at, I would say, the crawl stage, the crawl, walk, run in Rust and Windows. We're experimenting with the tool chain. We're looking at the code gen. We're trying to figure out, can this work? What does it cost to learn Rust? How would we port it? How would it work in the Windows environments, right? These are, we're talking about one of the most complex engineering projects on the planet, if not the most complex. And so making sure that Rust is going to work at this billion user scale is very important for these first stages. But our goal is to actually do this to improve security. But there are a bunch of different questions we need to answer to get there. So the first experiment was with Dwrite. And we had the opportunity to introduce what's called Dwrite Core, which is a portable version of the Windows Dwrite library. So we've had direct write in Windows for some time. But the introduction of cross-platform SDKs, things like WinApp SDK, that allows you to target different versions of Windows, has necessitated an undocked version of Dwrite that we call Dwrite Core. So we took and forked this version outside of Windows and essentially converted it to Rust. And so when you go and use an application, for example, like a Fluent Windows app that uses font parsing, it's actually today at least partially written in Rust. It's actually incredible. Dwrite Core is now 152,000 lines of code in Rust compared to 96,000 in C++ from just one cut. And so I'll talk to you a little bit about what that looks like. I'm going to skip through this, but Dwrite has a lot of different layers from shaping to parsing to layout. And we looked at different ways to overlay Rust with the goal of having as much safe code as possible and avoiding some of those memes you've seen where it's like, I wrote this in Rust, and it's a bunch of unsafe calls to C under the hood. We don't want to do that. So we were able to successfully integrate and interoperate, find different approaches for integrating C++ and Rust. One of the ways we do that is through public APIs. So there's actually a number of COM-like interfaces directly in Dwrite Core where you can call from C++ code directly into pure Rust. So that we didn't have to do things like have wrappers in C or C++. We're able to actually generate Rust code for the public APIs. So what went well is the language worked super well. This was a self-contained project, so Arden and team who did this actually really selected a surface. There weren't a lot of dependencies, and parsing was reported as incredibly easy by the team. And this is, I think, the thing that I was most excited about showing you as I'm running out of time here, is that performance increased 5 to 15%. So not only did we get memory safety, we got a boost in performance. So I think that, for a first crack, is actually pretty cool. And I'm sure the Rust crowd out there will say, see, I told you we can have safety and performance. That's right. That's right. This is a rough analysis of what it costs to do this. 2 months of dev time just to true type, another 2 months or so for shaping, another couple months for layout, and a few weeks for Unicode analysis. So roughly half a year or so of developer time to port, but for a surface that's notorious for security issues, 2 devs for 6 months seems like a pretty good value proposition. And now I'm going to jam through this. The second experiment has been with GDI and Win32K. We started again with a self-contained area called the region, which is a data type that models overlapping controls in the UI. You can actually see this here at the bottom. It's actually designed in the late 80s and 90s, so fitting we're here at this conference where it has that theme. It's in the Windows build currently, but disabled with the feature flag. But I'm told on good authority that I can announce here in Israel that this will be in insider previews shortly. So you will actually have Windows booting with Rust in the kernel in probably the next several weeks or months, which is really cool. Basic goal here was to convert some of these internal C++ data types into their Rust equivalents. So you can see here we have a bunch of private data types here in C++ that represent things like spanning controls, index into traditional array, and other constructs that are common to have spatial type issues. And we're able to replace those pretty simply with Rust native types like vec and result, which not only has memory safety, but has the ability to do better linting and analysis. And so progress so far is 36,000 lines of code in the Rust port. Perf is excellent, no regressions, and very few calls to unsafe code, at least in this analysis. And so one other thing I wanted to call out is there's actually a syscall in the Windows kernel now that is implemented in Rust. I don't know, I'm a Windows geek, so I think that's cool. So the next step here is Dwrite Core is shipping now, so you can work on that. Check that out if you want. I said the GDI regions are coming really soon. And we continue to work on CPU architecture, because as much as we love Rust, we know it's probably not the solution to rewrite the last 40 years of C and C++ code in Rust. So we will continue to look at broader approaches using what we learned from Chariot, memory tagging. You can go read some of the papers that our MSRC and Windows folks have written. We'll use these different approaches to continue to evolve our memory safety approach. And with that, I want to just point out, Windows is continuing to evolve. It's been around a long time. It will be around for a long time as long as we can keep going. So we are tackling the oldest and largest challenges. I've shown just a few of those today. We are even doing more. I wanted to bring this in, but I didn't have time. We are killing a number of notorious legacy attack surfaces, from NTLM to SMB v2. There's a lot of work happening there. And ultimately, killing bug class is our focus. You'll see probably less on the exploit mitigation front from us. So with that, I just want to say thanks, Tel Aviv, for the people who have waited. I appreciate that. And I did want to ask you one small favor. I have a really good friend who works in security in Redmond, and she's sick with cancer, and she really wanted to be here, so I want to ask you all to say, get well for her. So if you could, maybe on the count of 3, say, get well, Dia, and I'm going to send her the video. So 1 sec. 1, 2, 3. Get well, Dia. All right. Thanks, everyone. I appreciate that.